Hey, it's me, Moser. See? There I am. Okay, that's not really me. That's just me in my wildest dreams. So, here's me. And you're here because you're working on this worksheet about tolerance curves and how species tolerate the abiotic conditions in their environment. So let's just introduce this a little bit. Now, for some of you, this is going to be very self-explanatory, and you won't really need this video. But I want to walk through it. So when you look at any chart or graph, make sure that you read all the information that's there. So the graph on the first page is titled Boron Tolerance in Red Clover. So we know we're talking about red clover, and we know we're talking about how red clover takes boron, whatever boron is. It's a mineral. Anyway, the x-axis is labeled boron concentration in soil, and the units are parts per million. And the y-axis is labeled number of individuals. So you already know that wherever you are on the y-axis at the top of this curve is going to be the maximum number of individuals that you would expect to find. With a tolerance graph, we look at these divisions on the x-axis, and the ones that mark the boundaries of the green area, sometimes called the optimal zone, show us sort of the outer limits of where this species does best. The optimal zone, of course, is where the species thrives, individuals are able to grow, and they're able to reproduce, and so the population can expand. That's a good thing, right? Yeah. So if we look at the next set of divisions as we move out on this curve, we see that they cap the bottom of the yellow zone. The yellow zone is sometimes called the zone of physiological stress, and that means that when individuals of this species are forced to live in the conditions in that yellow zone, they're stressed out. They're under actual physical stress because they're not getting what they need. That could be a shortage of oxygen or too much oxygen. It could be a shortage of boron or not enough boron. It could be too much salt in the water or not enough salt in the water. The other thing that those divisions I've currently got circled do is mark the top of what we call the zone of intolerance, the red zone. The no-go zone, the zone of death. Below that bottom boundary for the zone of physiological stress, we tend to see individuals die. We tend to see fewer and fewer that can survive those conditions, and often that drops off even more rapidly, but we'll leave it as is. There might be a few hardy souls who can tolerate that zone of intolerance, but not a whole lot. Now, one thing that I don't think I mentioned was something about the zone of physiological stress. On some graphs, we'll see this divided into two sections, a yellow and an orange. In some, we just leave it as one section. But in this sort of borderline physiological stress area, the half of the zone of physiological stress closest to the optimal zone, very often individuals can still grow, but they can't reproduce. Life is okay for them. They can grow and they can eat and poop and do all the other things they need to do, carry out most of their life activities. But they're under enough physical stress, that they can't make babies, which means what's going to happen to their population? It's going to decline. The sort of outer edge of the zone of physiological distress is where stuff gets real. This is skirting dangerously close to the zone of intolerance, and in that lower part of the zone of physiological stress, we're going to see individuals who aren't even able to grow, let alone reproduce. They'll survive, but that's about it. They're not doing well. You don't want to be in that yellow zone, in the lower part of that yellow zone. So here are two graphs showing acidity tolerance of pH levels in two different species of fish. And you may be familiar with the brown carp. The brown carp is our friend that lives in lakes all over the place and rivers. They were an introduced species. And as you can see, they thrive and survive from a pH of 5 up to a pH of 10. That's a pretty big range. To get some idea, neutral plain water has a pH of 7. Now, on the other hand, we have the steelhead, the rainbow trout. Rainbow trout are a little bit more particular. And you can see that they thrive and do well in a pH of anywhere from 7 to 9. It's a much narrower range. Now, from 9 to 12, they survive. Individuals might even grow, some of them. But the closer we edge to 12, the less likely it is that even individuals will grow. And anywhere above 9, they're probably not going to be reproducing. Now, if we drop below 4, we see the same thing. And once we get above 12 or below 4, we see that they're dead. Compare that to the brown carp, who can survive, maybe not thrive, but survive in waters anywhere between 3 and 12.5. It's a much bigger range. So, what does this tell us about specialist versus generalist species? Well, the brown carp has a wider niche, wider tolerance range for pH, and therefore is probably more of a generalist. The steelhead is a little more particular, and we see this tendency again and again in species. We can also make some bets about what kind of water we would find brown carp in. Well, any place with a pH of between 5 and 10, and where we might expect to find good steelhead populations. Typically waters from 7 up to 9, and maybe even edging up to 10 or so. That's how you use a tolerance graph to make determinations about species, what they can deal with, and where they're happiest. If you have questions, email me.